Number 2, to solve by graphing y equals x plus 1 and y equals 2x minus 1, notice that the equations are in y equals mx plus b form, and it would be very easy to determine the slope and y-intercept. That would allow us to make graphs quickly. So let's start with y equals x plus 1. Looks like the m number in front of the x there would be an invisible 1. So this line has a slope of 1. Since we like to think of slope as a fraction, let's put that over 1. And then the b number helps us know what our y-intercept is. In this case, b is 1, so the y-intercept for this line is 0, 1. That means the line will start at 1 on the y-axis, and from there it'll go up 1 over 1. Keep in mind when you're graphing these systems of equations on MyMathLab, you'll need to click on 2 points for each line. So if I was on MyMathLab right now, I would click on the grid to activate it, choose the line drawing tool, and then click on maybe my y-intercept to start, and go up 1 over 1 and click that point. Those two will tell MATLAB where this line goes. And then we'll also need to graph the second line, y equals 2x minus 1. The slope this time looks like 2. And we want to think of that as a fraction, so let's put it over 1. And then the other number here, b, will tell us the y-intercept, in this case 0, negative 1. So let's start this time at negative 1 on the y-axis, and from there go up 2 over 1. Up 2 over 1, as many times as you like. Remember, you can also reverse that pattern if you want to draw dots in the other direction by going down 2 and then left 1. So if this same problem was on MyMathLab, I would again want to click the grid, choose the line drawing tool, click on 2 points, like maybe the y-intercept here, and then the point that I land on after I go up 2 over 1. Ultimately then we want to look and see where the lines cross. Looks like the point where they cross, the intersection, is at 2, 3. So we can tell from the graph the solution to this system is 2, 3. Be very easy to check. If I put the 2 in for x, plus 1 would make 3, and that matches the y value. And the 2 in for x value here, 2 times 2 would be 4, minus 1, also makes 3, which is the y value. Number 3 is a little bit trickier problem, because the first equation here is not in either of the forms that we've been accustomed to. And the second equation is also a little unusual because it has a y but not an x. So let's take one at a time. Let's start with the negative 2x plus y equals negative 5. Since it is in a bit of a strange form, maybe this would be a good opportunity to try rearranging and getting the y by itself so that it would be in y equals mx plus b form. If I want to get the y by itself, I would need to add 2x to both sides to get rid of that, which leaves me with y equals 2x minus 5. Now I can tell that m, in this case, the slope is 2. Let's think of it as 2 over 1. And b, the y-intercept in this case, is negative 5. So the line goes through the point 0, negative 5. Let's start on the y-axis at negative 5, and then from there we'll go up 2 over 1. As many times as we want. So that's a good example of how you can rearrange the equation, put it into y equals mx plus b form, and use that same shortcut for graphing, even when it doesn't look quite like that to start with. The second equation, y equals 1. is one of our special lines because there's only a y and not an x variable. What we know is every point on this line has a y value of 1. So 1, 1, 1, no matter what the x is, y has to be 1. So you could imagine any x values you want, like maybe a positive number, maybe a 0, maybe a negative number. And all of those will help us know exactly where that line's going to go. You might remember that when there's only a y and not an x, the line's going to cross the y-axis, and it's going to cross at this number, at the 1, which means in this case turns out to be a horizontal line. If there was an x only, that would have been a vertical line instead. So we can still look to see where the two lines cross. Looks like 3, 1, and that will be our solution. Few new tricks. Solving for y to make it look like y equals mx plus b, or remembering about our special lines, the horizontal and the vertical. On the next page there are a couple of systems for you to try. This would be a great time to maybe pause the video, try graphing each pair of equations and seeing where they cross. So the first equations are in a great form to just come up with numbers that add up to 4. Use that to graph our first line. And then come up with pairs of numbers that make 2 when you subtract. Use that to make our second line. Turns out these two lines cross at the point 3, 1. You might notice that 3, 1 was on both of my charts here, since it satisfies both of the equations. Number 5 is in y equals mx plus b form, so a great time to recognize the slope, y-intercept, use that to graph the equation. Same for the second equation, slope of 1, y-intercept of 2, makes the line here. Those two happen to cross at the point 3, 5. Try pausing the video again and seeing how you do getting started on the last two problems, number 6 and number 7. You'll find that they are some special cases and show us what could happen with the two lines. The two lines almost always cross at one point, like we've seen on all of our examples so far, but there's a little something else that could happen. Number 6 looks a lot like many of the problems we've done. We can begin by coming up with pairs of numbers that add up to -1 and using those points to graph that line. And then for the second equation, let's come up with pairs of numbers that add up to 5 and use those to graph the second line. 2, 3, 4. 2, 3, 2. Looks like we happen to have parallel lines. The lines are running at the same angle. They're not ever going to cross. So if the lines don't ever cross, that means there's no point that they have in common, or in other words, there's no solution. So this is one of the special things that can happen. If the lines are parallel and do not cross, then there's no solution. Number 7 is another example that's unusual, or one of our special cases. The equations this time are not exactly in either form that we're used to, so this might be a great time to try to get the y by itself. For the first equation, that would mean I need to subtract 4x from both sides. And that makes the slope -4. Then notice if you're thinking about y equals mx plus b, because there's no extra number being added on here, we would think of the b as 0. And that makes the y-intercept at the origin, 0, 0. So from there, we'll go down 4, right 1, and get our first line. The second equation, negative 8x minus 2y equals 0, is also one where we might want to solve for y and put it into slope-intercept form. So let me add 8x to both sides to get started. Negative 2y equals 8x. Oops, positive. And then to get the y all by itself, divide both sides by negative 2. So drop down the y, drop down the equals. Positive 8 divided by negative 2 makes negative 4. And drop down the x. So notice that this actually turns out to be the exact same equation. Still has a slope of negative 4, still has a b or y-intercept of 0. So when I go to graph that second line, I end up with the same line I had the first time. So these lines definitely do have points in common. In fact, every point along the line satisfies both of the equations, since the two lines turn out to be the same, which means that every point along the line is a solution. There are too many to list, so what we'll see instead is just a phrase like, this system has an infinite number of solutions, or maybe just infinite solutions. We're not saying that every single point is a solution, because this one here, for instance, is not on the line. But what we are saying is that every single point on the line is a solution. So there are way too many to list, an infinite number of solutions.